Hi everyone, it's Aviva, and this is going to be a new way I'm trying out to see if I can record video for you guys using this GoodNotes app. I'm going to try to be real explicit with it, see how it goes. You'll let me know if you hate it or love it. Anyhow, this is going to be part 1 of 2 for our Tuesday lecture, March the 17th. I believe. So I'm going to be working one and a half problems with you guys right now, which is the gravitational field of a ring of uniform density, and then the gravitational field of a disk of uniform density. It should take about 40 minutes, and then I'll do another 40-minute lecture separately, probably going back to the old way, because this is like the 4th time I've done this and failed. So if this doesn't work, I'm going back to old fashioned. Okay. Anyhow, I hope you all are well, and let's get going. So what I have pictured here is, in fact, a ring from 2 different angles. So I'm just looking here at this ring. This is kind of like the 3-dimensional view of it. So you can see by my second drawing that ring, again, a 1-dimensional object, think about it as a rod in a circle, is in the YZ plane. Here, the x hat is out of the board, which of course here you can see that dimension. And we're trying to find the gravitational field at some point P, as marked, from the center of the ring, kind of directly outward. So that's the setup, and what we're going to be thinking about this as is finding the gravitational field of the ring. We're going to be treating this as just a bunch of different point masses dm. Since this is a uniform density, what I'm really going to be thinking about this as kind of evenly spaced masses in a circle. Maybe one of them is an infinitesimal mass dm. And so I'm going to be treating this as just kind of integrating over point masses. And again, that's where this form comes from. I'm thinking about this as just a infinite sum, which is an integral of fields from point masses. So if I take a look here on my ring, let me kind of mimic what some of these point masses look like here. Little DMs all around the circle, uniformly spread out. If I focus on one of them, let me draw the line kind of between them. This would be kind of an infinitesimal field from one of those point masses. If I choose one down here, do the same thing. This would be an infinitesimal field from that point mass. And in fact, if I went around the full circle, I would be kind of tracing out this conic shape with all those little infinitesimal fields. And I think you can see that by looking at that for these little DGs. Here's 2 of them. What you're going to end up with is a component that points along, this is the minus x hat direction. And then they're also going to have components kind of what looks like they're pointing in the positive and negative y hat, but in fact, these are both kind of pointing radially outward. So these are like the positive r hat direction, but for now we're going to call it positive radial hat direction to distinguish from the plus or minus r hat, which is something we're going to be using. Similarly, this is going to be also the positive radial direction here. So minus x hat and positive radial. As you make your way around the circle, you can only imagine that all of those radial components are going to cancel. So this is my point P, and this represents maybe the radial component of a DG. As I make my way around here, you can see as I integrate around the circle, it's going to look something like this with components canceling. You know, for every component here, there'll be a component maybe here that exactly cancels it because of the uniform distribution in equal distances away. So at the end of this whole thing, I'm expecting my G net to point entirely in this direction, in the minus x hat direction, and all of the radial components cancel. Now, we could argue by symmetry, but instead we're going to prove that. Okay. So just to begin, let's look again at our formula. G of the ring at point P is going to be equal to the integral over all of these little point masses from dm. So treating these as point masses, I know the gravitational field of a point mass is gm r squared plus or minus r hat. So that becomes g times dm over r squared plus or minus r hat, where, again, I'm thinking about this, right, in terms of a bunch of little point masses uniformly distributed, and I'm summing them up effectively. So what I need to do to move forward is to find dm, to find r, and to find the plus or minus r hat direction, enter those into my integral, and then I'll be looking pretty good, sitting tight. I'm going to start with dm. It's actually pretty much the easiest here. Remember, dm comes from the density. So remember, this is a uniform, one-dimensional object. It's one-dimensional, meaning I'm looking at dm over dl. And since it's uniform, I can easily write down that this is equal to total mass divided by total length, as we proved in the last video. The total mass, m, is actually a known, so let me go ahead and write what our knowns are in this problem. Right here at the very top, we're going to know m, we're going to know the radius, and we're going to know x naught. X naught's going to be the distance away that point P is from the center of the circle. So let me see if I can draw it in here. So this is x naught. The radius, of course, will be the radius of the circle. And m will be the total mass of the object. Okay, so those are our knowns. So here in the denominator of my density, I have m as a known, and then the total length will just be the full circumference of the circle, 2 pi r, where r is also a known. So m divided by 2 pi r is a known quantity. So I'm going to focus on, dm dl equals m over 2 pi r, but I need to think about the dl portion. This is easy when I have a rod laying on the y-axis or on the x-axis, then it's dy or dx. But here we need to think about it a little bit. So if I'm going to go back to this picture of the ring, here it is, and I think about, one of the little point mass, dm, sitting here on the ring. Of course there's many of them, but let's just think about ours. And I think about the size. That's what dl is the size of that point mass. For us, though, we're going to say that dl equals something called ds, the arc length. So that's the size. That's the size of my point mass. So let me just kind of spread it out a little bit to make it look better. And if here's the center of my circle, I can kind of think about this little arc length right here where, we know arc length is radius times theta. Well, an infinitesimal arc length, where r is constant, is just r times d theta, where r is the radius, and then d theta would be this angle right here. So that gives me a value of the arc length. Getting rid of that radius really quickly. So, kind of also define this angle theta. You know, this is important because we are going to be integrating over d theta. It's actually the thing we integrate over for the ring, where theta can go from 0 to 2 pi, and that will cover the entire ring as we move around. So writing dl as ds, which is equal to r d theta, will allow me to integrate over the correct thing. So what I'm doing here again is writing dl equal to ds, which is r d theta in my density. And from here, I just readily get an expression for dm. So let me take that to the next page. And I'm going to go ahead and solve for dm from here. So dm, bringing the r d theta to the other side, m over 2 pi r, you can see that that dm is going to reduce pretty easily, canceling out these r's, to m d theta over 2 pi. Okay, that's it. I now know my dm in terms of constants that are known. Of course, m is known, and 2 pi is known, and the thing I'm integrating over, which is going to be the d theta as we move around the circle. So dm is known for me. Great. So I'm going to move on to find what is r. Then r, again, being the distance away from the point P, and each one of these infinitesimal little masses. So I'm just going to draw a couple of the masses on here again. I'm going to look at the different values of r that I can have. So here's one r, here's another r. These are just the ones kind of at the top or bottom, but all of these values are r right here. Again, just drawing a few of them in. There's some over here. You know, this is kind of scaled as a three-dimensional view, but maybe you're starting to understand just by looking at that r is a constant in this problem. One of the ways that I can see that is by kind of drawing this distance here, or maybe here. And although it might be hard to see, all of these green lines are just the radius of the circle right here. And if I recreate the triangle in question, I'm going to see that every single time for all of these values, I'm going to kind of come up with the same triangle. It's the same triangle for all dm's. Maybe you can convince yourself of that, but what that means for me is that r is in fact a constant. It's unchanging for all of them. I mean, it changes direction, but r is not the direction. That's the plus or minus r hat. R is just the magnitude of that distance, and it's a constant and the same for all of them. Constant because r and x naught are known constants in this problem and are unchanging. So right now we found r, looking pretty good. The fact that it's a constant means that if I look at g dm over r squared plus or minus r hat, that I'm going to be able to pull out that g, but I'm also going to be able to pull out that r squared as well, because it's a constant under the integral, so I'm pretty happy about that. I am anticipating having a 1 over r term in here, and once I do, I'll be able to pull that 1 over r term out, and that's going to make this one a cubed. I am anticipating it because it was similar to what we did last time with the rod. Okay, so let's keep going. Let's find the plus or minus r hat now. This one's a little bit trickier. Now, we've already talked about the direction and that of the gravitational fields, the little infinitesimal fields, and how they're changing. Let me kind of go back and get that color again to remind you. Going back to this picture above, you know, the little infinitesimal fields, they lie along that line of separation for all of these. And remember, what they're really doing is kind of tracing out this conic shape. And remember, just thinking about these fields, here's a DG. Remember, what I'm arguing is that they can be broken up into a component in the negative x hat and then a component in the radial direction, positive radial direction. So since that's the direction of the DG, that's also the direction of the plus or minus r hat. So again, I'm expecting this to trace out kind of a circle as you move around. Here's your point P. So how do I represent the plus or minus r hat? Well, one thing to kind of think about, so looking up at this triangle here, I'm going to draw that plus or minus r hat direction here. It does go along the line of r, is that I can break this up into a negative x hat and a radial component, and then use similar triangles to get the size. So you can see here that the plus or minus r hat is similar to this triangle that I've just drawn it on top of here, right? So these are similar triangles right here, plus or minus r hat, and the length triangle with r, and x naught. So because of that, I can use them. So let me define an angle here. I'll go ahead and call this angle alpha, because I've already used theta when talking about the thing that I'm integrating over. But this angle alpha will be the same for the plus or minus r hat here. And so right away, I can kind of write this as a component in the negative x hat direction and one in the positive radial direction. It's going to be cosine of alpha in the negative x and sine of alpha in the positive radial. And using the similar triangle above, I just quickly write it here. I can right away find sine of alpha and cosine of alpha equal to r over r and x naught over r. And I would be done by plugging those in, except for the fact that I have this radial direction in here. You know, we've learned that when integrating, that this is not constant, you know, under an integral. That as you move around, this changes with theta. So we actually need to find an expression for that. So before I plug in sine alpha and cosine alpha, I'm going to find an expression for the radial direction. Good times. So probably the easiest way to do that is to look at kind of our original picture of the ring. So I had talked about, if this is a little dm that we're looking at, that this angle here is theta. Well, just for reference, this would be the positive y hat and this would be the positive z hat direction here. Kind of going back to the first page picture. So drawing the positive radial direction, it's going to look like this. This is it, the positive radial. And I can break this up into a component along the y hat and the z hat, which are constant under the integral. I mean, the y hat and z hat are, and maybe make my integral a little bit easy. But to do that, I have to recognize that this angle is theta 2 in this triangle. So I can represent the radial in terms of a minus z hat component. In fact, it'd be minus cosine theta z hat, and a positive y hat component, positive sine theta y hat. And then I'm done. Z hat and y hat are constants under the integral, and we're integrating over d theta. So my expression for the radial direction is complete. At this point, what I need to do is to take this, and this, the sine alpha, cosine alpha, and this radial direction, and to take all of these and plug them into here. So I'm going to do that on the next page. So I might have to flip back for reference. Let's see, minus cosine alpha x hat plus sine alpha radial. Oof, good luck to me. You know what? I got this fancy tool. Let me use it. Ooh. Okay, that's all right. Okay, let's try this out. So the plus or minus r hat then, minus cosine alpha, minus x naught over r x hat, plus sine alpha, which is r over r, in the radial direction. And that's it. That's actually finished. My argument is later, all of this will end up being 0. And we'll only be left with this minus x hat component. But let's see that come out of the integration. So, gravitational field of a ring. G integral dm over r squared plus or minus r hat. Now, remember the r squared is constant. Can come out, and I'll plug in r in just a second. Remember, r was the square root of r squared plus x naught squared. Just write it up here. My dm, I'll be inputting now as m over 2 pi times d theta. That's the dm. The r squared's already been pulled out, and that leaves the plus or minus r hat to insert. Sorry, I ran out of room. Okay, my bad. But let me pull all the constants out. So for instance, this is a constant, can be pulled right out. Also, you can see that there's this 1 over r factor that I was alluding to that can be pulled out, and I can make the squared into a cubed. After I'm done with that, I'm going to be left with 3 different integrals, an x hat, a z hat, and a y hat one. So I'm going to go ahead and factor everything I can out and reduce this down to the 3 integrals. But before I do, I should remind you guys that we are integrating over d theta, and remember that's from 0 to 2 pi. That's going to be for all 3 integrals. And so gravitational field of the ring can reduce to gm over 2 pi r cubed. I'm still waiting to put an r. And that's going to be minus x naught, x hat, which are both constants, integral of d theta from 0 to 2 pi. I'll also have a positive r z hat. Oops, and when I said positive, that's actually going to be negative. Let me fix that. Minus r z hat. And there'll be integral of cosine theta d theta from 0 to 2 pi. And then I'll have a positive r y hat, integral of sine theta d theta, all from 0 to 2 pi. Great. I can definitely do this now. This integral is just 2 pi. This integral you'll see is going to be 0, and this integral also 0. Cosine theta over the full circle and sine theta over the full circle are 0. So at the end, only that minus x hat component is going to survive as promised, and the radial direction ends up being 0. So at this point, I am going to go ahead and plug in my r value into my equation and reduce this down. G of the ring is going to be equal to gm over 2 pi r cubed. So a square root cubed is going to be to the 3/2 power. And I'll have a minus x naught x hat, all times 2 pi. So you can see that these 2 pi's are going to cancel out. And then finally, at the end, this is the field of the ring. Now, all of this is done for you on pages 82 to 84 of the notes that I made for you guys. So as a reference, you can go back and look there. I do want to spend just a little bit of time kind of reducing this down. For you guys, before we move on. So final answer. And what I want to kind of take a look at is, does my answer make sense? And so I have a little check that I do. And specifically in this case, does my answer make sense when I go from having a ring, right, of radius r, if I let r equal to 0, and of course don't forget that ring has a mass m, what that looks like is that I'm just recovering a point mass. So if I check my answer for r equals to 0, I should be expecting the geometry of my object to disappear, and the gravitational field of a ring should reduce to the gravitational field of a point mass. Now, the gravitational field for a point mass, that would be at some point P, a distance of x naught away, and it should be gm over x naught squared in the minus x hat direction, because the full gravitational field would just look like this, right? Be pointing totally in the minus x hat at point P from m. R would be x naught, and m would be m. It's pretty straightforward. So does it reduce? Well, I'm just going to plug in r equal to 0. Here it is, 0, shoot, you guys, sorry. 0 squared plus x naught squared to the 3/2 power in the x hat. So you can see that this denominator here is going to reduce to x naught squared to the 3/2 power is just x naught cubed. And so this becomes minus gm x naught over x hat divided by x naught cubed, or as expected, the gravitational field of a single point mass, a distance of x naught away. So I'm feeling pretty good about that. Right. Nice. So the next part of the problem is also done for you in the notes, page 84 to 85. What this is looking for now is to look at the gravitational field of a solid disk, a two-dimensional object, from rings. So the idea is, now that I know the gravitational field of a ring, right, now that I know this value, I can think or take these rings and just kind of add up a bunch of them to make, this makes a disk. So if I just kind of integrate all of these rings, so I would need to know the field of a ring of small mass dm, but I could add them up to make a disk. So since I know the field of a ring already, what I'm going to argue is that each one of these little rings is going to have an infinitesimal mass dm. not a point mass, but a point ring, which makes no sense, but a very, very thin ring with a very, very small mass. And then I can add those up by integrating to get the gravitational field of a disk. So our disk now is going to have a radius of r. So now this is kind of this is a 2D object. Here's my disk. Looks like my other picture, except for now this is a 2D disk. It has a radius r. And what I'm going to be saying is that I'm going to be trying to, make this disk up as kind of a bunch of different rings that I'm adding up. Each one of these rings, each one of these rings is going to have a radius of little r. And really, I'm going to be integrating over dr. So let me say it again. The outer radius is a constant. R is a constant. It's known. The total mass of the disk now is also going to be known. And we're still going to know x naught is still known because the setup is similar. We're going to have the disk, just like we had the ring in terms of the way it looked. It's literally going to be the same picture. Same picture, but now it's a disk. Y, Z, X. Here's my point P. And I'm a distance x naught away. And now, what is the gravitational field of the disk at P? So to allow this to happen, I'm going to look at the gravitational field of the ring, and I'm going to say, I'm going to let M become an infinitesimal mass. Like one of these rings has an infinitesimal mass. And that means the gravitational field of the ring at point P will become an infinitesimal field of the ring at P. And so the gravitational field of the disk will look like this. Minus x naught g. My mass will become a dm all over x naught squared plus, and this is where things are a little different. So let me highlight it. This is not big R anymore because this is the radius of a ring, and we're allowing that to vary. So at this point, a lot of things are constant in this problem. X naught's still a constant, that's known. G is still a constant. X hat is a constant. X naught is a constant. Of course, this minus 1 is a constant. At this point, I'm going to be integrating over dr to make these rings. So r is not a constant, but I'm assuming dm is going to have to be written in terms of dr and known values. So really, all I have to do is to find dm, and then I'm pretty much ready to go. So let's move to the next page. Okay. All right, so let's find dm for this problem. So this is now going to be dm from the density, but we're talking about an area, so a disk, a two-dimensional object. So this is dm dA. This is a uniform disk, so it's going to be the total mass over the total area. In this case, that's m divided by pi big R squared, which is the radius of the actual disk itself. At this point, I could solve for dm, but I would realize pretty quickly that I don't really understand this d area. And what it's supposed to represent for me is how does the area change as I make these rings become a disk. And so one way to think about it, if you remember, we have our ring, we have our disks, and we have these little rings inside of it that are changing. And each one of these rings has a dm. Each one of these rings also has a dA associated with it. And as I'm integrating radially outward, the d area changes as follows: 2 pi little r times dr. So this would be the circumference times the thickness of the ring. So in a way, this is dr, and 2 pi r would be this circle times its thickness, and that's how each ring changes its area under the integration. Or you can kind of do this mathematically. You say the area of one of these little rings that I'm integrating over is pi little r squared. dA dr is how they change radially. And so this will allow me to get dA equal to 2 pi r dr specific to the problem that we're working. So in total, my dm is m divided by pi big R squared. Again, that came from the total radius, times the d area, which is 2 pi little r dr. You can see that factor of pi is going to cancel. And finally, my dm is going to be 2mr dr divided by big R squared. At this point, I am sticking this into my equation above. But I'm going to pull out as many constants as I can first, actually. So let me get the minus x naught g x hat out of there. And then I'll put in my dm. Divided by x naught squared plus little r squared to the 3/2. And since I'm integrating over dr, here are my r's. I'm going to go ahead and say the integration is going to be from r equals to 0 to r equals to the outer radius of the disk. So those are my dr integration. Everything else in here, again, is a constant, so I can easily pull out the 2m over r squared, but not the x naught squared in an easy way. So I'm going to do this via a u substitution. X naught squared plus r squared equals u, and then du dr. I know you guys can figure it out from here in terms of integrating, but at the end, the gravitational field of the disk should be minus 2mg x naught over big R squared, 1 over x naught minus 1 over the square root of x naught squared plus r squared. And that's it. In the notes, there's a very good example, I believe on page 85, of reducing this down via the polynomial expansion, or the binomial expansion, to look at the limit, what happens as, believe r goes to 0. Anyhow, take a look at the reduction at the check. Very interesting, and I'm going to turn this off, and hopefully I've successfully recorded this whole lecture, and this should be part 1 of 2. Okay, talk to y'all soon, bye.